Hello AP Chemers. Today we're going to talk about real gases versus ideal gases. Now, of course, we know that there is no such thing as an ideal gas. All gases are real. However, some gases behave more ideally than others, and other gases behave more real than others. What does that mean? An ideal gas is a gas that follows kinetic molecular theory. Remember, kinetic molecular theory has several statements and it also has several assumptions. Ideal gases also follow the ideal gas law, which is PV equals nRT, meaning that if you were to use PV equals nRT to find one of these variables, whether it's pressure or volume or amount or temperature, if it's a gas that is more ideal, then the value that you solve for is going to be pretty accurate. It's going to be very close to the correct value. If it's a gas that is more real, not as ideal, that means that when you solve for one of these variables, your answer is not going to be very accurate. It's going to be a little bit off from what the true value is. And so the more ideal it is, the closer the value is to reality. And the reason is because KMT and PV equals nRT make several assumptions. So let's talk about those several assumptions. So there are two main assumptions. The first assumption is that ideal gases, their volume is negligible. So the volume of the gas particles themselves is negligible compared to the container. Now you can always make that assumption because the gas particles are extremely tiny. There are huge spaces between them. And so compared to the container, the gas particles are almost negligible. So we say that their volume is, zero. And so we really take just the volume of the container into account when we use PV equals nRT. Now that's, of course, not true because real gases are made up of particles or matter, which has mass and volume. And so, of course, real gases have volume. So because they have volume, to make up for that, we have to subtract the volume of the gas particles themselves from the volume of the container if you want a more accurate result. The other main assumption that KMT makes is that ideal gases have no intermolecular forces. They do not exert any forces on each other. There's no attraction. You can usually make that assumption because gas particles are very spread apart, and so because they're so far away from each other, their intermolecular forces are insignificant. But of course we know that real gases do have intermolecular forces. And so to make up for that attraction, we add the pressure caused by that attraction. So if we make these corrections, we would get a much better answer. It's just that it's a lot of work for an insignificant difference. Because again, you can always make those assumptions since gas particles are so far apart, their volume is negligible and their intermolecular forces are negligible. Now also, we said that some gases behave more ideally than others. And so which gases would be more ideal? The gases that are more ideal are the ones that follow KMT and its assumptions more. And so KMT is assuming that gas particles don't have volume. And so if your gas particles have a pretty small volume, then they would behave more ideally, since we're assuming their volume is zero, basically. Also, KMT says that ideal gases don't have intermolecular forces, and so if you have really weak intermolecular forces, then again we can say they're insignificant or negligible. So the gases that behave more ideally would be the ones that are smaller and the ones that have weaker attractions to each other. If you have the opposite, so if you have particles that are really large in volume and have very strong attraction to each other, those would be the ones that would behave less ideally, or would be the ones that are more real gases. So let's look at this question here. It says, which gas behaves more ideally? So helium or argon? The correct answer would be helium for two reasons. The first reason is helium has smaller volume. Its particles are smaller. We know that based on the periodic table and atomic radii, and therefore the volumes. The second reason is because helium has weaker intermolecular forces. Now, both of these have London dispersion. They're nonpolar. However, with London dispersion, the more electrons, the more the dispersion, meaning the stronger the attraction. And so helium, because it has less electrons, has weaker attractions between its atoms, versus argon has more dispersion because it has more electrons, so stronger attraction. And so helium is smaller in volume and weaker in its attraction or intermolecular forces, which makes helium more ideal. What does that mean? That means if you were to use PV equals nRT, let's say to solve for pressure, if you're given the other variables, if you do a calculation for helium gas, when you solve for the pressure, you would get a more accurate result, an answer that is closer to the real pressure of the gas. Compared to argon, you would get a pretty close value, but not as accurate as you would for helium. Let's look at B. So methane, CH4, or NH3. That one is a little bit more difficult. Now, carbon is a tiny bit larger than nitrogen, but they're very, very close in their radius. They're right next to each other on the periodic table. Nitrogen's tiny, tiny bit smaller. Also, NH3 has 3 hydrogens, whereas CH4 has obviously 4 hydrogens, and so, having 3 hydrogens is a little bit smaller than having 4 hydrogens, and so overall, NH3 is a tiny bit smaller in volume than CH4. However, they're pretty close. They're not, very far apart in their volume. So let's look at intermolecular forces next. CH4 is nonpolar. It has London dispersion forces, which are the weakest of the intermolecular forces. NH3 has hydrogen bonding, which is the strongest of the covalent intermolecular forces. So their intermolecular forces are significantly different. And so based on that, I would pick CH4 as behaving more ideally because it's significantly weaker in its intermolecular forces. Their volumes are somewhat comparable, but in intermolecular forces there's a big, big difference. Let's look at C. Helium or water? In this case, the answer is helium for 2 reasons. Smaller volume, much smaller volume than water is, and much weaker intermolecular forces as well. Helium again has London dispersion, whereas water has hydrogen bonding. So definitely helium in this case. So most of the time, if you're asked which one behaves more ideally, typically it will be for both reasons, that it's smaller and weaker intermolecular forces. However, something like B, that one, the size was about the same, or the volume was about the same, but it was the intermolecular forces that determined it. So we said that the nature of the gas itself can determine whether it behaves more ideally or less ideally. Now let's look at what if you had the same gas but at different conditions. Now KMT, or PV equals nRT, works under most conditions. Again, under most conditions you can ignore the volume of the gas particles and their interactions or their attractions. However, under three conditions, KMT fails. The values that you get for it are not accurate at all. And those three conditions are high pressure, low temperature, and small volumes of the container. So let's look at each of these. First is high pressure. High pressure means a lot of collisions. So if you're under high pressures, that means you have a lot of collisions between your particles. If you have a lot of collisions between your particles, that means the particles are colliding more, so they're spending more time close to each other, and so in this case their IMFs become significant. If they are spending a lot of time close to each other, then their attractions become significant. Let's look at the next one, low temperatures. Low temperature has to do with the speed of the particles. So low temperature means slower particles. If your particles are moving pretty slow, that means that, again, they will spend more time close to each other, and so again, your intermolecular forces become significant, so you can't ignore them anymore. Finally, smaller volume of the container. So if you have a container that's pretty small and you have a bunch of gas particles in it compared to a much larger container with those gas particles in it, if you have a large container, the volume of those gas particles is negligible compared to the volume of the container. But here, the volume of the gas particles becomes significant compared to the volume of the container. So at small volumes, the volume of the gas particles themselves becomes significant. Okay, so what if you have one of these three conditions where KMT fails, you have high pressures, low temperatures, or small volumes of the container, or you have a gas that just does not behave very ideally. Its particles are really large in volume and it has very strong attractions. So what do? If you use PV equals nRT, then you're not going to get very accurate results. And so we correct PV equals nRT. We fix it. So how do we fix it? Instead of just using PV equals nRT, what we'll do is we will fix the volume. So we'll take into account the volume of the gas particles themselves. So to do that, instead of V, we are going to use V minus B times N. So V is our regular volume of the container. B is called a van der Waals constant. And it's different for each gas. Every gas has its own van der Waals constant. If you look at the last page of your notes, you will find a table that has values for those van der Waals constant for different gases. The units for B are liters per mole. And then N is the number of moles, like we're used to. Okay, so that's to fix the volume. Let's look at the pressure. So because gas particles do have intermolecular forces, we got to make up for that for the pressure. So instead of just P in PV equals nRT, we use P plus A times N over V squared. So P is your normal pressure that you would read. N is the number of moles, like always. V is the volume of the container. And A is another van der Waals constant. And again, it depends on the type of gas it has. So if you look at that table on the back of your packet, you will find different values for the A constant. The units for A are liters squared times ATM per mole squared. Now remember that this fixes the problem of the volume being ignored. And so if you consider different gases, B is going to be different depending on the volume of the gas. The larger the gas particles, the larger B is going to be, so that it fixes for that problem being ignored. If you look at A, this expression is fixing the intermolecular forces being ignored. And so the stronger the intermolecular forces for that gas, the larger the A value is going to be. So let's put all this together. So if you plug in this instead of V and this instead of P into PV equals nRT, here's what you get. You get P plus A times N over V squared, this whole quantity, times V minus B times N is equal to nRT. This is called the van der Waals equation, and it works a little bit better than PV equals nRT. You can use it for whether the gas is ideal or real. It will always work. It will actually give you a better result if you use this one. It's just that if the gas behaves pretty ideally, then if you use this or you use this, you're probably likely to get about the same number. So it's much easier to use this than it is to use a more complicated equation. This equation, by the way, is on your green sheet, just so you know, so you do not need to memorize it. So here's the table for the van der Waals constants that you have in the back of your packet. So again, remember A fixes the IMFs being ignored. B fixes the volume being ignored. So let's try this problem. It says predict the pressure of 1.25 moles of hydrogen gas in a 2-liter container at 37 Celsius. And we want to do that both as an ideal gas and as a real gas, meaning that as an ideal gas, we can just use PV equals nRT. As a real gas, we'd have to use the long van der Waals equation. So the reason why I want you to do that is to calculate it using both and then compare your values there. So let's start with the ideal. So PV equals nRT. And so you would say P is what we're solving for. The volume is 2.00 liters, is equal to N is 1.25 moles. R in this case, you can use whichever R you would like. I'll calculate my pressure in ATM, so I'll use 0.0821 ATM times liters per mole Kelvin. And then the temperature, remember you gotta convert it to Kelvin, so 310 Kelvin. So my pressure that I calculate in this case would be 15.9 ATM. Now let's try it with the real gas equation, or the van der Waals equation. So the van der Waals equation is P plus A times N over V squared, that times V minus Bn is equal to nRT. Let's plug in our values. So P is what we're solving for, plus A, this is hydrogen, so if you look it up on the table, A is 0.244 ATM times liters squared over moles squared. That was our A. Then times N, which is 1.25 moles, divided by the volume, which is 2.00 liters. And then that's squared. And then this whole quantity times V is 2.00 liters minus B is 0.0266 liters per mole times 1.25 moles and so that is equal to nRT. So N is 1.25 moles. R, let's use the same R so we can get ATMs. So 0.0821 ATM times liters per mole Kelvin. And then 310 Kelvin. By the way, I guess we have to use ATMs, like the R for ATM, because this value right here is in ATM liters squared per mole squared. If they give it to you in something else, then you'd have to use different R accordingly. So if you solve this whole big equation for P here, you would end up with the pressure equaling 16.1 ATM. And so this is the answer if you use the van der Waals equation. This is the answer if you use the real gas equation. So they're, I guess, relatively close to each other. But if you had to pick a more accurate answer, it's definitely the 16.1 ATM. Out of the three conditions, 310 Kelvin, that's not a very low temperature. 2 liters is not an extremely, small container. I would say 16 or 15.9 ATM, that's a pretty high pressure. The pressure in a regular room is about 1 ATM. And so that's 16 times that. So I guess, that is a relatively high pressure. But still, 16.1 and 15.9 are, comparable answers. So to review what could be asked of you on the test. So first of all, you could be asked, what is the difference between a real and an ideal gas? So you'd say an ideal gas follows KMT and its assumptions, whereas a real gas doesn't. So the two assumptions are that KMT says ideal gases have no volume, but real gases do, and that KMT says ideal gases have no intermolecular forces, but real gases really do. Another question that it could ask you is, which of these two gases behaves more ideally? So you'd pick the one that has smaller volume and weaker intermolecular forces. Another question could be, under what conditions does the ideal gas law fail? And so you would tell me low temperatures or high pressures or small volumes of the container, and I could ask you why, and so you would explain each of those. Another question that you could be asked would be to actually use the van der Waals equation to calculate one of these variables, just like we did. So that's pretty much everything that you would need to know about the difference between ideal and real gases. All right, hope you have a great rest of your day. I will see you later.